Okay, welcome everyone to the second day of the crypto workshop at Fox 2021. We have two fantastic talks in this session, one by Nguyen from Stanford and one by Rachel Lin. And then we'll conclude in the afternoon with another talk by Hotek, and then we'll do an AMA with me and Amit. So I hope everybody can join us in the afternoon as well. Okay, so with that, let's get started. So the first talk is by Nguyen from Stanford. So Wilson, looking forward to your talk, and the floor is yours.
Cool. So I'll be talking about a new cryptographic primitive, or sort of new cryptographic primitive called functional commitments. This is joint work with Dan Bidet and Alex Odsmir. So we will first describe what we call a uniform application problem. So imagine there is a bank with some secret FICO credit scoring algorithm F. It wants to keep this algorithm secret so that individuals cannot game to get better credit scores. So here are individuals, Alice and Bob. Alice will request her credit score by sending over her financial data, and the bank will apply the secret FICO credit scoring algorithm on her financial data and return back the credit score to Alice. Bob also sends over his financial data and receives his credit score in return. Now, this is expected operation because the assumption is that Alice and Bob will receive their credit score based on the same secret FICO credit scoring algorithm. But what if the bank is somehow malicious? Let there be two different functions, F1 and F2, in which F1 is an algorithm that gives like very terrible credit scores, and F2 gives really nice credit scores. So based on different inputs from Alice and Bob, maybe the bank decides to apply the two different functions. And so this is unfair to Alice because she receives a credit score based on a very unfair algorithm, while Bob receives a really positive credit score. So the issue here is that the same function is not being used for both Alice and Bob. So that's an issue of uniform application. Say we had an imaginary way to restrict the bank to a single function. There are still ways that the bank can be malicious. So say the function is not just of Alice's and Bob's financial data, but also includes some type of secret auxiliary information. So imagine that Alice is a part of some class of people, class A, and Bob is a part of a different class of people, class B. We can see that after requesting financial data, they receive basically two different algorithms applied on their credit scores, applied on their financial data. And so the issue here instead is that the function takes in private inputs that are not made public or are not aware to Alice and Bob. So what can we use to restrict the bank to using a single function? So we'll discuss first maybe a related primitive and see whether the structure is something that we want. So a commitment scheme is a pair of algorithms. One, the commit algorithm, which takes in a message and some randomness R and outputs C, a commitment. You can think of these as just binary strings. So imagine the analog is putting a message in an envelope and then having an envelope be the commitment. There's additionally an algorithm called verify, which takes in a commitment C, a message M, and the randomness used previously to commit, and output 0, 1, whether the commitment coincides with that message and randomness. So you can think of it as opening the letter and confirming that the M as input to verify is actually the M sort of contained in the commitment. It has two properties. The commitment scheme is binding. You cannot produce strings C and different tuples, M and R, such that both verify, so both output 1 when input on the verify algorithm. And it's hiding in the sense that C reveals nothing about M. So looking on the outside of the envelope, you can't infer or distinguish what M's are inside of the envelope. But the issue here is that this does not support any functionality native to functions just yet. Maybe we can somehow commit to a function and then expand the functionality to allow sort of selective openings to different inputs. So what do we want a functional commitment scheme to be, right? So a prover has some type of function in some function family, and it samples randomness R. With a functional commitment scheme, it's able to commit to this function and send it over to the verifier. And the verifier wants to know what is F selectively opened at some input X in the input space. The prover calculates Y equals to F of X. And then after some thinking and computation, generates an evaluation proof. So you can think of this proof, pi, as a proof that the function coinciding with the commitment is equal, when evaluated on X, is equal to Y, and that it knows some randomness and the function such that C coincides with that function combined with that randomness. And then the verifier, using the commitment, the input X, the Y it received from the prover, and the proof pi is able to check the proof and decide whether it accepts it or not. So maybe with this functional commitment scheme, we can solve the uniform application problem, but also enable other functionality that we have not seen prior. So let's think back to the bank with this secret FICO credit scoring algorithm F. Imagine there are users Alice and Bob and the bulletin and a public bulletin board. You think of this as maybe maintained by the government, or maybe it's on a blockchain, but it's some type of public bulletin board that everyone has access to. So the bank produces a commitment to their credit scoring algorithm and posts this commitment to the bulletin board. Alice and Bob are able to read this commitment from the bulletin board and keep it in their memory or their local storage. Then they can request for their financial, using their financial data, their credit score, and the bank returns back their credit score, which is the evaluation of the secret FICO credit scoring algorithm on X, and accompany it by a proof, an evaluation proof, which we saw on the previous slide, that the evaluation does coincide with the function inside the commitment. So now, functional commitments also enable a different sort of functionality. So say there is some trusted auditor, in the sense that the bank trusts this trusted auditor. You think of it as maybe some government regulatory body. The bank will give this function and the secret FICO credit scoring function and randomness to the trusted auditor. The auditor will take the commitment from the bulletin board and keep it in their memory. And now the trusted auditor can check two things. Is C equal to the commitment based on that function and that randomness? And is F a fair algorithm for some notion of fairness? Maybe it could be like, is this algorithm legal? But this is based upon the regulatory rules of the auditor. And then they can sign the commitment and post it to the public bulletin board so that Alice, Bob, and other customers are able to at least have some sense of trust that the credit scoring algorithm used is fair in some sense. So functional commitment schemes, do they exist? What are some examples? And what is our work in context? So examples of functional commitments, polynomial commitment scheme. is an existing works in which a prover commits to a polynomial and is able to verifiably open at any x in the field of the polynomial. So you can think of it just as evaluating a polynomial verifiably at a point. Verifiable random functions are also an existing line of work in which provers commit to a key in some type of key space and are able to verifiably open the pseudo-random function keyed on that key on some input x from the input space. So our work is we construct functional commitment schemes for, or a functional commitment scheme for arithmetic circuits of bounded size, such that you can verifiably open the circuit at any input x to the circuit. See our paper. So related work, there is a mirror notion of input hiding functional commitments in which you commit to a private input x and then open at a public function f of x. Oh, sorry, f. So you can think of this as their work as you commit to x, and then you just simply open, you sort of open to an evaluation using a public function f. We call these input hiding functional commitments, while our notion is you commit to a private function f and you open on a public x. There's also a line of generic zero knowledge proof systems in which it's an interactive argument between randomized algorithms prover and verifier, in which the prover has access to instance x and a witness w, and the verifier has access to an instance x. And the prover wants to convince the verifier that x and w is in the relation, as an x is in the language, while keeping w private from the verifier. So these actually both imply functional commitments by the use of universal circuits and standard commitment schemes. But the transform is incredibly inefficient. We have the universal circuit overhead, and also we have to prove the preimage of a standard commitment scheme, which you can imagine is trying to prove the preimage of some cryptographic hash function. So let's start off with potentially a more efficient starting point. So preprocessing ZK SNARKS are an existing line of work in which it's a zero knowledge proof system for circuit satisfiability, or you can think about it in this way, in which you take an input x and an input w, which you can think of the instance and witness, to a public circuit C, and it determines whether C is equal to 0 or 1 when evaluated on those inputs. So what we can do is we can take a circuit C, input it into a pre-processing algorithm that somehow summarizes the potentially large circuit C into a proving key and a verifying key, in which the verifying key is constant size with, also with this security parameter sort of term. You can think of the verifying key as an efficient summary for the circuit. An efficient summary for the circuit that the verifier can just take instead of the circuit. So the prover is given the prover key and outputs a proof pi, and the verifier takes in the verifying key and the proof pi and outputs 0, 1. So maybe we can somehow use this efficient summary, the verifying key vk, to produce a functional commitment. Maybe the summary itself could be the functional commitment. So let's do that. Let's try that and see what goes wrong. So the prover has some function in some function family. It produces a circuit which does not take any witness inputs, just the input x, and it's set to be that function evaluated on x. We pre-process this circuit to produce a proving key and a verifying key, and then we send over the verifying key as the commitment to the verifier. The verifier wonders what f of x is equal to, and the prover computes f of x and sends over the evaluation, and also a proof pi that c of f evaluated on x, which is summarized in that verifying key, is equal to y. But this scheme is actually, and the verifier verifies that proof. But the issue is that this scheme is actually broken, and we'll go over why it's broken. So the first problem is that the verifying key may not be a hiding commitment to F. So remember, in a commitment scheme, we want it to be binding, as in you can't find another function, another randomness such that they verify with the same commitment, but also hiding, in the sense that they should not reveal anything about the function. So if I had some verifier who maybe it's the commitment is in the set of circuits C1, C2, it turns out that preprocessing is actually a deterministic process. So they can just run the preprocessing step for both circuits they're suspicious of, and then are able to check whether that commitment aligns with those verifying keys. The problem too is that the proof pi from the preprocessing SNARK may not actually be a zero knowledge argument for the circuit itself. It's meant to be zero knowledge for the witness for that NP relation, not necessarily the circuit. It turns out that these two problems are actually easy to solve for preprocessing SNARKs, but check out our paper for more details on that. So the big problem is that the verifying key may not represent a valid function at all. So we can take this in two possible methods. The verifying key may literally be trash bytes, as in the prover just sends over something that was not in the image of the preprocessing function. But also, it could commit to relations or circuits themselves that do not represent valid functions. So here we have a circuit with a public input X and private prover input W, and it outputs W as the output of the circuit. So why is this not a valid function? So you can imagine for a singular X and two different Ys, we have that C of X Y1 is equal to Y1 and C of X Y2 is equal to Y2. So through the preprocessing ZK SNARK, the prover is able to convince the verifier of two different evaluations based on the commitment they received prior from preprocessing. So you can see that we have two different Ys and the same X, so vertical line test fails, and this indeed is not a function relation. So how do we go actually proving that the verifying key represents a function F in some function family, big F? You can think of this as a public function family. So let's look back at the original issue here. So we have something, a circuit, when preprocessed, does not provide a function relation. So imagine that we're somehow able to prove that it is indeed a function relation. So what would that look like? So let's look at the relation in particular described above. So it's all tuples X and W such that C of X W is equal to W, in which W is private to the verifier. So you can see here that this is definitely not a function relation. And so it's because preprocessing ZK SNARKs support a wide range of NP relations, which do not necessarily represent functions. So maybe we can somehow restrict to NP relations which represent functions. So what we want is a proof of function relation, which proves that the underlying relation represented by that verifying key is a function. So what would that look like? So this is mirroring the previous slide we had. So the prover has some function, randomness R. It has some type of encoding of the function, which we denote by these brackets here. They pre-process this function with this randomness to produce proving key and verifying key. This verifying key is sent over as a commitment. The verifier questions whether the underlying encoding is actually a function in some public function family. And the prover, after some computation, sends over a proof of function relation pi, which shows that the pre-processing was actually run on an encoding of some function from the function family, and that F is indeed in that function family. And then the verifier can compare with the commitment, check the proof pi, and see if it agrees or not. So first, let's unwrap preprocessing ZK SNARKs a little bit more. So as we mentioned earlier, a polynomial commitment scheme is the prover is able to commit to some polynomial and then open it up at any point in the field. We have this notion called polynomial interactive oracle proofs, which we will define in the next slide. They plug these both into a compiler and are able to produce preprocessing ZK SNARKs. And so we will take a look at polynomial interactive oracle proofs. So a polynomial interactive oracle proof system, or PIOP for short, is an interactive argument between two algorithms, a prover and a verifier, in which the verifier is given oracle access to polynomials pi, in which the prover has the plaintext representations of these polynomials, x and w, from some NP relation. The verifier sends over some strings m, and the prover is able to send over oracle polynomials q1 through qn. And the verifier anytime is able to query these any of the oracle polynomials originally sent, originally it has the PIs, and also any oracle polynomial that the prover sends during the interaction. It's able to query at any point and get back these answers. And this goes on for some amount of rounds, and then the verifier outputs some decision bit about whether x and w is in a particular relation. So let's take a concrete example. So here is the zero test, which is an example of a classic polynomial IOP. So we want to prove that some polynomial f is 0 over some multiplicative subgroup H generated by omega. And so notice that these are indeed the roots of this polynomial, xn minus 1, which we'll call the vanishing polynomial for H. So the prover is given the plaintext representation of f, and the verifier has oracle access to the polynomial f. So if indeed f is actually 0 on H, then it can divide f of x by xn minus 1 and compute a quotient, which it sends over to the verifier. The verifier then samples some randomness from, samples a random element from the field, and then checks the following identity. It queries f, q on the random value r, and then also computes the vanishing polynomial evaluated on r. And so if this identity holds, the soundness of the test overall holds by Schwartz-Sippel lemma. So what relations actually represent functions? So there is a preprocessing ZK SNARK Marlin, in which you can think of the verifying key as polynomials which encode matrices A, B, and C. So the proof of function relation needs to prove that A and B are roughly strictly lower triangular, and that C is a diagonal matrix. You're just going to have to believe me about this. And that these happen to actually capture arithmetic circuits as well. You're going to have to believe me on that. Plonk, you can think of it as a preprocessing ZK SNARK in which the verifying key represents polynomials encoded as a permutation, which somehow represent a circuit. And in this case, the proof of function relation needs to prove that the permutation encodes a valid circuit with no hidden inputs. So now all we have to do is somehow test that the verifying keys indeed encode valid matrices or valid permutations, which satisfy these sort of restrictions. So we're going to go over the diagonal test for the sake of time, but the rest of the test, you can just check out our paper for that. So the diagonal test. So first, let's understand how matrices are encoded as polynomials. So consider two multiplicative subgroups, H and K of order 3 and 4, row and column, they are polynomials which encode row and column indices, and value encodes the values of the non-zero entries. And so let's take a look at the first entry B, whose indices are 0 and 1. We can see that row and column evaluate to the generator of multiplicative subgroup H raised to the 0 and 1 power, which are just simply the indices of B, of the element, non-zero element B, and then the value evaluates to B. And then let's look at the next element, C, whose indices are 1, 1. The evaluation of the row and column polynomials are indeed just the powers of those indices. And then the value is C, and so forth. And so if we look at what a diagonal matrix looks like, for the sake of the proof of function relation, we also require that some amount of the entries in the top left of the diagonal matrix are also 0. So let's just put a 0 there. So if you have a diagonal matrix, the encoding looks like this. It turns out that the row polynomial is the exact same as the column polynomial, and that the row polynomial whose evaluations over K follow this particular pattern. It's a geometric sequence which starts at gamma to T and has a common ratio gamma. And then at some point, it evaluates to gamma to the 0 and then just keeps on being gamma to the 0. So let's look at that a little more closely. Oh, sorry. So the diagonal test simply is just checking if row is equal to column and that row's evaluations over the multiple subgroup K is indeed the aforementioned geometric sequences that we described earlier. And also there are some checks applied on the value polynomial, which we will not discuss. You can see our paper for that. So the first check is an equality check. And so we want to check that row is equal to column. And so we want to show that for all K in the multiple subgroup K, that f of K is equal to g of K. You can think of this as the row and column polynomials. So let's define a new polynomial, h, which is f minus g. So we can see that if f of K is equal to g of K, only happens if h is also 0 on that element. So in order for f to be equal to g over the multiplicative subgroup K, it must be that this polynomial h is identically 0 over the multiplicative subgroup. And so we simply have to run the before mentioned 0 test on the polynomial h. And so that suffices to check equality. So now we'll go over how we can check the geometric sequence, which we call the geometric sequence test. So let's look at the evaluations of row over K. We can see that let's do some splitting here. And so the first half of elements is gamma to T plus 1, gamma to T plus 2, all the way so forth to gamma to n minus 1. And then the rest of the elements are 0. And then if we take a look on the right side, all the elements are 0. And then the bottom half, it's just gamma to 0, gamma to 0, gamma to 0. And so we can look at this as 4 different geometric sequences in which the first one has an initial starting element gamma to the T with a common ratio gamma. The bottom starts with an initial element 0, has common ratio gamma. The top right has initial starting element 0, common ratio 1, and the bottom initial element gamma 0, common ratio 1. So we can see that these are 4 different geometric sequences in which there are 2 sets of geometric sequences that have the same common ratio. And so is there a test to test whether the evaluations of a polynomial are 2 geometric sequences with the same common ratio? So let's take a look at that. So say f has these properties here. We can see that every evaluation times beta is equal to the evaluation of the previous element times gamma. So maybe we can come up with a sort of inductive argument. We would ideally like that the evaluation of the next element in the sequence is equal to the evaluation of the previous element in the sequence times gamma. So maybe we can check the following polynomial identity. F of beta x, which is the evaluation of f on the next element, is equal to the previous element times gamma. And so if we check this identity by an inductive argument, we can guarantee that every element is this next element times gamma. But there are a few issues with this. There are no guarantees that the starting elements in the geometric sequence are actually gamma to t and 0. Imagine the starting elements were -1, then the sequence would be completely different. And so what we can do is the verifier, since it has oracle access to this polynomial, can just query these points individually. So now that we know that the starting elements are gamma to t and 0, and we know that every previous element must be the next times gamma. So maybe we're done here, but there's also another issue. And that's that the inductive argument breaks on these sort of like transition areas between the two geometric sequences. We can see that gamma to n-1 is definitely not equal to 0 if you multiply it by gamma, and then also for the wraparound in the multiplicative subgroup. And so what if we just explicitly include a backdoor for those two cases in which the induction breaks? So we have the initial identity that we want to check. And then we can just simply include two sort of inductive backdoors here. And so since there are no zero divisors in a finite field, it must be that one of these cases is 0 when evaluated over k in the multiple subgroup k. And so we can see that either the next element is equal to the previous element times gamma, or I must be the particular element which breaks the induction, either one of those two. And so then the geometric sequence test just consists of testing that this identity is true over f. And so we can run the 0 test we had earlier to check this identity here. So then in summary, the test to test whether the encoding of C as row, column, and value polynomials are indeed a diagonal matrix consists of the prover interpolating and sending two polynomials, h1 and h2, such that their evaluations are the geometric sequences that we saw earlier. And we have to run equality check to make sure that row is equal to col, and then that they're both equal to h1 plus h2. And now we run the geometric sequence tests on both h1 and h2 to confirm they're indeed the geometric sequences that we expect to see. And so that by itself then convinces the verifier that row and column are indeed the geometric sequence that we need it to be. And then there are a couple other tests that are necessary, but you can just see the paper for the rest of the tests. So bringing it all together, a poly-IOP plus a proof of function relation, and also polynomial commitment schemes imply functional commitments. So the commitment phase consists of the prover committing to matrices A, B, and C, which are restricted to strictly lower triangular and diagonal matrices. They encode these matrices as polynomials, row, column, value, and then use a polynomial commitment scheme to commit to these polynomials. And then they send this commitment to the verifier. Then we run a proof of function relation as a polynomial IOP, in which the verifier has oracle access to the row, column, and value polynomials. And so why would it have oracle access? So given that we have a commitment to these polynomials, the verifier can actually open up these polynomials at specific points, and the prover can send a proof that these polynomials evaluated at those points are indeed actually consistent with the commitment sent earlier. And so we just run the proof of function relation, which is the strictly lower triangular test for A and B, and the diagonal test that we went over for C. And then we can run Marlin, which was the pre-processing SNARK we mentioned earlier, that happens to be a PIOP before compilation using polynomial commitments, which convinces the verifier that X and Y, like the function encoded, indeed on X is equal to Y. And that is a functional commitment. So the takeaways are here's our paper link. We produce the first efficient function hiding functional commitment to arithmetic circuits. We construct a proof of function relation for the pre-processing SNARKs Marlin and Plonk. Check out our paper for the full protocols. And there are several open questions that I wish could be explored and solved. So could there be other proof of blank relations? And so what we have is a commitment to an arbitrary arithmetic circuit in which people have an interest in making sure that they have sort of uniform evaluations of this circuit. And so maybe you, instead of proving it's a function, there are other properties of these functions that you would like to provide sort of zero knowledge, non-interactive proof for. And so you think maybe I can prove that the algorithm that I've committed to is fair without having an external auditor be able to see what the function is. And so maybe there's proofs of fairness, maybe there's proofs of some other properties that are desirable. And also, so what that would look like is that the bank, instead of sending over the function and the randomness to an auditor, can just directly send a proof of fairness to Alice. Then Alice can check with the commitment that she has that F is a fair, that C was produced through a valid commitment process, and then F was a fair algorithm. And then maybe there are other new primitives or protocols implied by functional commitment schemes. These are quite powerful. You can think of functional commitment schemes as, instead of sending polynomials as oracles, maybe you can send bounded sized functions, due to their representation as arithmetic circuits. And so maybe binding a prover to a particular function or a particular strategy enables new other primitives or protocols. Yep, and that's my talk.
Great, thanks, Wilson. Sounds good. I guess we have a few minutes for questions. So why don't I kick it off and see if anybody else has questions? So I guess one question that comes to mind is, can you say a little bit about how, like, there's a lot of steps in these proofs. Can you say a little bit about how practical this is? Like, if you wanted to implement this or to build this for like, realistic functions, like, I don't know, maybe some simple machine learning model that you want to evaluate or so. Is there a way to commit to the machine learning model secretly and then show that you evaluated that model correctly? Is that going to be realistic?
Oh, sorry. So the transform currently is a little bit expensive. We proved it as a theoretical sort of commitment scheme so far to prove possibility, but there are plenty of optimizations that we did not take currently. Did we not do in the previous paper. I think the overhead over Marlin is maybe in the range of like, I have to recall the particular numbers, but it's probably within 13 to 30 times overhead between a single Marlin pre-processing proof. But there are a lot of optimizations that we didn't take. For example, it turns out that you don't even have to do a diagonal test. You could actually just pre-process a row and column polynomial because the verifier already knows what these polynomials should be. And so maybe you can just avoid having to do some of the tests. So currently, if I want to commit to GPT-3, maybe that's not realistic, but maybe simpler algorithms like as the FICO credit score, some bail decision algorithm, Something a lot simpler, I think, would be more efficient. Oh, sorry, would be practical at the moment without any optimizations. But otherwise, there's a little bit more work to do in order to make it efficient for general practical use.
Great. Any other questions or?
Yeah. So all of these are in the random oracle model. Is that right?
Yeah. So in order to make it non-interactive, yes, we use the Fiat-Shamir transform.
Cool.
Yeah, like many SNARKs are in that paradigm.
Yeah. So right. I believe Marlin and Planck also use Fiat-Shamir.
Great. Let's see. Okay, so in that case, and are there any other questions? Maybe I'll just ask one more question.
Oh, sorry, I forgot to mention that all of our protocols are also constant round and constant query. So you don't get like log n rounds. You don't get that loss from Fiat-Shamir, like too much of a loss, hopefully.
Yeah. Yeah. All right. Sounds good. In that case, I just want to make sure that we start the next talk at the right time so that people who want to join at 9:45 will not be missing the beginning of Rachel's talk. So let me ask you one more question. So you kind of covered how to do these, the proof that the functions really are functions. You covered that for these Planck and Marlin. These are like two standard pre-processing SNARKs, but there are others, right? There are there are SNARKs based on hash functions like Stark and such, or even other pre-processing SNARKs altogether. So how do you think that these techniques would generalize to other pre-processing SNARKs?
So as of now, these techniques are very particular to how the pre-processing SNARKs encode their circuits or their relations as polynomials. And so for different pre-processing SNARKs, that target potentially different relations or different encodings, you have to sort of tailor the proof right now to the particular relation, but maybe there is some type of generic proof of function relation that doesn't use the encoding protocol as a non-black box sort of thing.
Yeah. So for SNARKs in particular, there's probably more research to do here to figure out how to use that for a functional commitment. Yeah, cool. Okay, sounds good. Thank you very much, Wilson. I know you're also a little sick, so thank you for giving this talk while not feeling well. Much appreciated. And so with that, I think we can switch over to our next speaker. So